In this episode of STEP series, let's take a look at this question from the second paper of 2015. The first part requires us to use calculus to show that x minus ln 1 plus x is positive for all positive x. When it comes to calculus, it could only mean differentiation and integration, and in this case, we should go for differentiation. We can see that f prime x is 1 minus 1 over 1 plus x, and this is always larger than 0 for any positive x. This means that x minus ln 1 plus x is an increasing function, and since f0 equals 0, we can conclude that fx is always greater than 0 for all positive x. This allows us to write x bigger than ln 1 plus x for all positive x. Next, we need to use this result to show the inequality given. To match the formula, it would be sensible to let x equals 1 over k. Doing so, we get the inequality 1 over k larger than ln 1 plus 1 over k. The right hand side of the inequality can be written as ln 1 plus k divided by k. And crucially, using the laws of logarithm, we can separate the logs into ln k plus 1 minus ln k. After we get this expression, we just sum both sides of the inequality from k equals 1 all the way until n. Doing so, the right hand side collapses and cancels out, leaving only the last term, ln n plus 1. So, we have proven the result as desired. As always, the second part of the question is more challenging. Let's look at what the question wants us to prove. It wants us to consider x plus ln 1 minus x and use this to prove an inequality involving squares of fractions. Let's get inspired by what we have done before and differentiate this function. We see that we get 1 minus 1 over 1 minus x. However, it's rather hard to say whether this is larger or smaller than 0 for all positive x, since x minus 1 happens to be a vertical asymptote. What we can do though is to investigate the behavior of 1 minus 1 divided by 1 minus x for x between 0 and 1. Since later, when we substitute x equals 1 divided by k squared, this will fall between the range of 0 and 1 anyway. Now, using a chain of inequalities as shown, we see that for x in between 0 and 1, 1 minus 1 divided by 1 minus x will be less than 0. Since the derivative is less than 0, we see that our function x plus ln 1 minus x is a decreasing function between 0 and 1. f0 is 0. So for any x larger than 0 and smaller than 1, since the function is decreasing, we can write down this inequality. Substituting x equals 1 divided by k squared and doing the same thing as before, we get 1 divided by k squared lesser than ln k squared minus ln k squared minus 1 after we split up the log. The next bit is slightly clever. We need to use the property of logarithms again to write ln k squared as 2 ln k and split up ln k squared minus 1 into ln k minus 1 plus ln k plus 1. We are now ready to take summation on both sides. Mindful that our inequality earlier required x to be lesser than 1, we can sum from k equals 2 onwards to infinity. Doing so, we see that many of the terms cancel out in a telescoping series, leaving only ln 2 at the end. And finally, we add 1 to both sides. So the summation starts from k equals 1 instead of k equals 2. And we have proven the result as desired. I guess the difficult part of the question is twofold. While the splitting up the logarithm part seems pretty reasonable, this might not come so easily during an intense 3 hours exam. What is more delicate though is how we handle the boundary value of k equals 1 separately, as we require x to lie between 0 and 1 strictly. I imagine it will be easy to just paint everything using a broad brush of telescoping series and not caring too much about k equals 1. But in STEP exams, mistakes like this cost points, however minor they seem. Therefore, it is important to keep a cool head throughout the exams and be mindful of tiny details like this, although sometimes it can be easier said than done. Well, we have come to the end of the video, and I will see you in the next one. Until then.